Good afternoon, and welcome to the Loeb lecture series in physics. It's a pleasure and honor for me to introduce Ali Yazdani, a colleague and friend, professor of physics from Princeton University. Ali has made a lot of really significant contributions in the area of strongly correlated electron physics, and as the name implies, correlated electron physics involves correlations amongst electrons, and it's therefore a little bit surprising that Ali has managed to really learn so much about these systems from doing local probing of these systems using a scanning tunneling microscope, where he's looking basically at the properties on an atomic scale and figuring out some of the underlying properties on larger scales. This kind of inverse problem of figuring out what the bulk properties or the large-scale properties of the system from the small-scale properties is really an art, and Ali has mastered this art. Over the years, Ali has developed and constructed some of the most sophisticated scanning tunneling microscopes known to us. In particular, he's been able to construct microscopes that are able to look at the same cluster of atoms as one varies relevant parameters like temperature and magnetic field. And this allowed him to really study some of the different phases and how the system undergoes transitions from one phenomena or one behavior to another as magnetic field and temperatures are varied. Ali's interests are very, very broad. He has impacted many areas of correlated electron physics, and a few examples are heavy fermion systems. He has been able to image localized electronic wave functions in magnetic semiconductors. He's looked at Kupret superconductivity. He's looked at topological insulators and more recently topological superconductors. And this first Loeb lecture will be really about realization of topological superconductors and observation of some of their exciting properties. His work has awarded him a lot of awards and distinctions, and I don't have time to really specify all of them. It's a very long list. I'll only mention two. In 2012, he became a fellow of the American Association of the Advancement of Science, and in 2015, he became a fellow of the American Academy of Arts and Sciences. So with this, I'd like to ask you all to join me in welcoming Ali to give his first lecture.
Thank you very much. Thank you. Thanks very much, Amir, for that kind introduction. It's a great pleasure to be back here at Harvard and to give these lectures, and I'm especially honored to be here on the pumpkin drop day, which I very much enjoyed. I was very worried that this involved somehow the speaker, but this did not happen. So, as Amir mentioned, my group does scanning tunneling microscopy experiments, and I'm going to explain to you what that is in a second. But the topic of this talk, as Amir mentioned, is the study of topological superconductivity. And in particular, what we are interested in is to try to find a very exotic quasi-particle, which is called the Maya Rana fermion. So let me begin this story by focusing first on what is a Maya Rana and who was Maya Rana, and why has this been a subject of interest not only to the condensed matter physics community, but also the physics community broader. So of course the work of Maya Rana goes back to the 1930s, where Maya Rana was basically looking at the Dirac equation very soon after it was written down by Dirac. And as you know, Dirac wrote these equations to basically teach us how we can get complex fermions. And from these equations, basically, he predicted the presence of antiparticles. And what Maya Rana did is he looked at these equations, and he realized that although Dirac had looked at complex fields, he could basically find a solution to the Dirac equation where the fields were real. And in the sense of the particles that we're used to, Dirac fermions are basically invented to give us basically charge and also give us both particle and antiparticle. And now if you have a solution that could be a real fermion. Of course, it has the bonus that if you take a complex conjugate of a real object, it's equal to itself. And in this way, Maya Rana basically put forward the possibility that we could have fermions in nature that are neutral and are their own antiparticle. So of course, this has fascinated people for a long time. And equally fascinating is actually Maya Rana person himself, because soon after he wrote these ideas down with actually Fermi published for him, he actually disappeared. He took a boat from Sicily to the mainland in Italy, apparently, and he never got off the boat. And for as long as basically since 1938, people have been wondering what happened to this man. So today I'm going to talk to you about the search for Majoranas in a little bit outside of condensed matter physics and in condensed matter physics. And hopefully at the end, I will also tell you some things about what we have found out about what has happened to the man. After all, it's Halloween, so we have to bring something scary into the story. So soon after, Maya Rana basically proposed this idea that you could have a fermion that can be its own antiparticle. People wondered whether neutrinos were actually Maya Rana fermions. And in fact, this question has not been settled to this date. And there is a lot of effort in the community of folks looking at neutrinos to try to determine whether a process which is called the neutrino-less double beta decay can be observed in nature. Now, if this were to happen, basically as this diagram shows here, sort of not super clearly, it shows that if neutrinos are their own antiparticles, the two would annihilate, and you basically get two electrons coming out of this double beta decay. And if you can observe this, one of the interpretations would be that neutrinos are Majoranas. And there are a lot of folks out there trying to look at this kind of process with very precision measurements underneath the ground, looking at very low background type of physics to study neutrinos. Now, we do condensed matter physics, and in condensed matter physics, we have this kind of a long tradition going back to Lev Landau, who basically introduced the notion of quasi-particles, the notion that in metals or in materials, you can have excitations, collective excitations or individual excitation of an electron system, in which these excitations can behave like the particles that we do quantum statistics of every day as free particles, but now these are bound inside the solid. In fact, this is perhaps what we find most fascinating about doing condensed matter physics, is that the solids give us the opportunity to engineer our universe and basically create for ourselves different kinds of quasi-particles. So it shouldn't surprise you to start thinking about, is it a way that in which we can create a Maya Rana fermion inside a solid? So let's look at what we need to do this, and this has kind of been the excitement on the past few years. Now the trouble is, when you start with a solid, what you're dealing with is basically mostly complex fermions. We are just basically given electrons or holes, which are antiparticles of electrons. How do you start with this and make yourself a Maya Rana fermion? So you're trying to make a real object. So if you were trying to make a complex object, you add two real ones with the I. So you can basically judiciously combine your complex objects, complex operators, to make a real operator. So if you could make an equal mixture of electrons and holes, if you like, this object can basically behave like a particle that is its own antiparticle. Now, how do you do that? How do you combine electron and holes in an equal mixture? So this is where superconductivity comes in. So let me just remind you, superconductivity is the phenomena where you have zero resistance. You also have magnetic expulsion. But the key ingredient for superconductivity is the fact that the electrons basically pair up to make bosons. And basically, if you can think of it as Bose condensation of these electrons. And in the simplest case, you have spin singlet pairs of electrons making your superconducting state. It's a perfect fluid. Now, what does this have to do with electrons and holes? Well, you can think of if you added an electron to a superconductor, or electron-like excitation, which we call a quasi-electron excitation, this can basically get converted into a hole if the number of those Cooper pairs was not conserved. And this actually turns out to be a key concept in superconductivity. The number and the phase of the superconductor are conjugate variables. So if you have a phase-coherent state, the number of Cooper pairs, if you like, is not something that you think about as a constant. So you can see in this sort of cartoon, superconductivity gives us an ingredient to combine a particle and a hole inside the metal, which is an electron and a hole-like excitation. Now, more rigorously, many of you are familiar with the Hamiltonian we write down when we write down the BCS Hamiltonian, which tells us the state of superconductivity by pairing electrons together. And many of you know that when you want to diagonalize this Hamiltonian, you would introduce operators which are known by Bogoliubov operators, introduced by Bogoliubov first, which basically combines the electron and hole-like operator to diagonalize this Hamiltonian. So we already know, we are sort of on our way to create this object by combining an electron holes by thinking about a superconductor. Now, but it takes a special kind of superconductor to do this. Because if you could create these excitations like the one I have depicted here inside the superconductor, what happens is that these excitations always go in pairs. So it's true that there are mixtures of electrons and holes, and there are equal mixtures of electrons and holes, but they're in fact not their own antiparticle. They come in pairs where the state above and the state below, there is a solution with positive energy and negative energy. And these two solutions always go in pairs in a superconductor. Now, normally a superconductor doesn't have these things because it has an energy gap, and that energy gap is required for it to basically behave as a superconductor, to protect the state of basically having no resistance. Now, I'll show you how we can actually create such states inside a superconductor. But what we're looking for is something more special. We're looking for something that is exactly its own conjugate operator. And this would have to be a state that sticks to zero at zero energy, and it has no partner. Okay? So it turns out that throughout condensed matter community, people who study the quantum Hall physics and people who study unusual superconductors, they have found examples of exotic superconductors which may possess such zero energy modes, these zero energy modes that are Maya Rana fermions. But the field really came to a sort of a more exciting area by the fact that there was ideas that came forward that you can perhaps engineer materials using ingredients that didn't require complicated electronic interaction, which you did not know how to theoretically model. Basically, the idea that sort of pushed this field forward came from Alexei Kitaev, who in a paper which is, I think, only 3 paragraphs long, he basically introduced this idea that what if we consider electron pairing in a very, very simple system in which you have a chain of atoms, if you like. And this chain of atoms, basically, electrons can hop between them, and that's this term in the Hamiltonian. And then, of course, you want to pair electrons. But what he introduced in this model was the idea that let's forget about the spin of the electron. Let's think that the electrons are somehow spinless. Now, it turns out that's a key ingredient in this model, because if your electrons don't have spin, and you want to pair them up to make this singlet state that's required for pairing and superconductivity, you have to make the orbital part of the wave function of this pair such that basically it has the right antisymmetric property. When you exchange the 2 electrons, you get a negative sign. And the only way you can do that is if you basically pair them in a p-like fashion. This is p-like orbital, which basically gives you a plus and a minus. And this basically preserves the antisymmetric property of the pair wave function. So now, what Kitaev did is that he solved this model. The solution to this is simple enough that I sometimes have assigned it as an exam problem, which is you have to make an interesting transformation where you take the electron and you split it apart into a pair of Majoranas. Okay, we talked about how we're going to make Majoranas out of electrons. So here we have electrons. We can basically write them as if they were made out of two Majoranas. Okay, you can think of a Majorana as half a particle and half a whole. Okay, and if you make this transformation on this Hamiltonian, what Kitaev showed, surprisingly, that this Hamiltonian has basically two kinds of superconductors in it. So what does that mean? So you have superconductivity where electrons are paired up inside this chain. And you can think about taking an electron and breaking it apart into two Majoranas, okay, each one. And allow me to show this picture, which is sort of you think about the way you break up an electron into two Majoranas. Now, just cartoonishly, you can see that I can take an electron on every site and split it into two Majoranas. But I can do this thing where I take half an electron from this site and half an electron from the site next door and make that a single electron from two halves of two Majoranas, which are on different sites. Now, if you looked inside this wire, you wouldn't be able to, unless you do some very sophisticated experiment, you wouldn't be able to tell this kind of superconductor from that one. But if you looked at the edge of this wire, basically you see that half of an electron or half of a hole is basically left hanging there.
Can you have an odd number? Is that possible to create?
No. So, fortunately so. But you basically can think of this. You can look at single sites. There are different kinds of models you can look at in single sites. But this transformation you can take basically for any number of sites, and it would work. Now, as I just mentioned, if it's a superconductor, electrons or holes are mixed together. So this thing at the end is both half an electron and half a hole. And this is what you would go looking for if you could look at a Majorana basically hanging at the edge of this topological superconducting phase. Now, this is what's fascinating about this Majorana in the condensed matter setting is that it's very different than the one you would look for as a free particle. First of all, they always come in pairs. Okay? It's because we started with an electron or a hole in a solid, and we basically are cutting it in half. Okay? So it's as if you put half an electron here on this side, half on the other side. So this is a single state which you can occupy or unoccupy. Okay? So it's not an ordinary fermion because it's not a local object. Okay? And this is where the story of a Majorana in a condensed matter setting gets even more interesting than just an object that is a quasi-particle that is its own antiparticle. Because if I have a set of two Majoranas, okay, I can think of, in time, taking this pair of Majoranas and moving one member of a pair around another member of the other pair. And depending on how I do this operation, the phases that the electron wave function or this Majorana wave function picks up would be different depending on this braiding process. So this is why we in the condensed matter community are very excited to try to create these Majoranas in a condensed matter setting, because it would be a first type of fermion which will have a non-abelian statistics. All right. And this non-abelian statistics and this braiding is one of the ways in which people are considering to make new kind of computation possible. So this Majorana state can be itself occupied or unoccupied, but these braiding operations corresponds to the kind of spin, the kind of quantum computing steps that you would take to create very complex, basically, entanglement between these different sets of Majoranas. And this is something that's been one of the goalposts of this field, is not only to engineer these Majoranas, but also to braid them. So that's the motivation for why we are looking to create these things in the laboratory. But now let's go back to Kitaev, who gave us this recipe. What he requires is like a one-dimensional system, like this chain of atoms. But what we require is to make electrons basically pair up such that they're in this p-wave channel. And the way you do this is if you somehow can make the electrons be spinless. So how do we do that? So an idea that came forward the last few years with the discovery of topological insulators, which you might have heard about, but I'm not going to get into the details here, is the fact that there are states inside solids which, because of spin-orbit interaction, the electron's spin and its momentum are tied together very strongly. So let me show you how this comes about. And this is basically one of the proposals put forward, inspired by work of folks that basically discovered topological insulators. Now, normally you have electrons moving along a wire, and their energy momentum would just be a parabola. Okay? And if you're a spin up and spin down electron, you wouldn't care if you have no magnetic field present. And these would be a doubly degenerate energy band of this one-dimensional system. Now, if you have heavy elements, the spin of the electrons and the momentum of an electron gets locked together. And the way this happens is that basically this band structure gets shifted. The electrons would spin up or spin down, gets shifted along the momentum direction. And if you apply now a magnetic field at the same time to this system that's made out of heavy elements, the electrons that are moving along this wire basically have this characteristic that they have these two energy bands. But in both of them, the forward-moving electron and the backward-moving electron have their spin and momentum lock in opposite orientation. But what's key here is that this spin and momentum basically are overdefined. If I basically tell you the momentum of the electron, you would know what its spin is. So in a sense, you can just forget about spin in the problem. And it was theoretically predicted that if you put this nanowire in contact with a normal superconductor, it would create this topological superconducting phase. Because the electrons that you're starting with, basically, they don't have a description that the spin is even necessary. So this is a picture of Delft in Holland. And they've basically been looking for Maya Rana using basically this theoretical recipe. And a few years ago, they succeeded to basically fabricate, using nanofabrication techniques, the exact recipe that the theorists sort of predicted or proposed. So you have this wire is sitting next to a superconductor, and there are a lot of other diagnostic tools around this. And the key thing here is this part of the wire is also connected to a normal metal. And they're using basically this electrode to sense what happens at the very edge of this wire. And in this experiment, they measured the rate at which the electrons go between this contact and that one. This is like a conductance. And they apply a voltage, which is either they're drawing current that way or the other way, or they're making electron-like excitations or hole-like excitations into this superconducting nanowire system. And what they saw was a zero energy peak as they tuned the magnetic field to a particular value. So this was a very exciting development, and this is where my group got interested in this field. And for us, when you look at this complicated structure and this measurement, there is a question of, well, do they really know that this Maya Rana is really living at the edge of this wire? How do they know that? This is a rather complex device. And the interpretation of these experiments depends on where the current flows and what other kind of electronic states do you have in this circuit.
And there are no other mechanisms for getting a peak at zero voltage?
There are lots of mechanisms, as you well know. There are mechanisms such as a celebrated Kondo effect that can give you a zero energy peak. There are mechanisms by which you can have disorder, and it can give you a zero energy peak. So we got motivated to do this because we wanted a system that was atomically clean, and we can look at it and assess issues about disorder. We wanted a system where we could actually image and see this energy mode is really bound to the end of the wire. And the reason we are motivated to do that is because we have the tools to look at both the structure of the material and its electronic property using the scanning tunneling microscope. So let me just briefly tell you how this works. You have an STM. These are the type of experiments done here, as well by Jenny Hoffman's group, where you bring a sharp metallic tip near the sample. Electrons tunnel between the tip and the sample. You raster the tip across the surface, often keeping the tunneling current constant. And the tip follows this trajectory, which gives you information about the constant electronic density of state. It also gives you information about where the atoms are. Now, you can park the tip at a given pixel on this picture and basically record the rate at which electrons come from the tip into the sample or vice versa. This is called spectroscopy. And this is very much like the experiment I showed you in those devices, except it's spatially resolved. We can go to every location and perform this experiment, like this is a spatially resolved measurement of a semiconductor. And when I say spatially resolved, is you can take a particular energy of electrons, whether 0 or some other energy, and ask, how does this look like in real space? So this is a lot of information can be obtained from these type of measurements. So it can give you the structure, it can give you the distribution of energy of electrons, electronic density of electrons, a function of energy, and their spatial dependence, and the connection between them and the structure of the sample. Okay? And we use this to, as Amir said, this is what we do for a living. We use this to study a lot of different type of materials. And I'll be talking about some of these examples throughout my stay here this week. For example, we use some topological system materials, or even looking at the quantum Hall states are some of the recent example of work that I'm going to talk about in the next 2 lectures. All right, so we've been looking for Maya Rana in Princeton, and this has been a very big group effort. And let me tell you who are the people who've done all the work. The chief partner in crime here is Andre Bernovic. No, he's not Maya Rana, but he could be inspiring to be a Maya Rana-like character. He's a very bright theorist we have. And he and I have been thinking about the system I'm going to tell you about, which is an alternative way of realizing Maya Ranas. And the folks who have done a lot of the bulk of the work, Gian, Stefan, and Ilya, done the initial experiments. And more recent experiments have been led by Ben, who came from Amir's group, as well as Malika, who was a student at MIT and came through Amir's group, who have done some of the recent experiments. And towards the end, I hope to show you what some new exciting stuff that they're working on together with Sangjun and Yonglong. In addition, we work very closely with folks that do electronic structure calculation of real materials, Alan McDonald's group in particular. So we came up with a completely different way of doing this. And we thought about what will happen. We wanted, if you look at this previous proposal, you needed electrons to experience a process by which their spin somehow defined their, was something you could take out of the problem. Okay, but it's still superconductivity play a role. So it turns out that you can use magnetism, actually, which is usually you think about as a very bad thing for superconductivity, as I'll explain in a second, to actually create this topological superconducting phase. So let me tell you how we do that. So let's start very easy. We just think about, I put one single magnetic atom in a superconductor. What does that do? Well, a magnetic atom in a superconductor, at a minimum, you can think of it just creates an exchange interaction with the electrons. So electrons, which are basically like to pair up in this singlet state, one of them would be attracted, the other one would be repulsed. You can think of this as breaking pairs of electrons. But if you ask what are the excitation spectrum of this system, what happens is that it creates for you this kind of in-gap, basically, neutral excitation, these Bogoliubov excitations that I told you about, but it creates a localized one living right near the magnetic impurity. So it creates a state, a single impurity creates a single state that lives inside the superconducting gap. It's these pairs of Bogoliubov states. And remember, what we need to do is have a situation where we end up with a zero energy state, which is this Maya Rana. And in fact, many years ago, when I had more hair on my head, I actually did this experiment where we put individual magnetic impurities on a superconductor, and we used the tunneling microscope to look around these impurities, in fact detecting these states that are living inside the superconducting gap, which are basically not Majoranas, but these are states that we call Shiba states, and they are neutral quasi-particles that are trapped around the individual magnetic impurities. So of course, the obvious question was, okay, if these states can be at these values, maybe they can be driven to zero. And if Kitaev wanted us to do a chain, let's think about what a chain will do. And then the moment we started thinking about the chain, we realized, oh, there is a way in which you can get spinless pairing. So let's think about a chain of magnetic atoms, but not put them all oriented the same way, but have a canted angle between these magnetic sites. And I put these on top of a superconductor. And the superconductor has these electrons that are paired up in spin up and spin down. So if these two pairs of electrons, they don't like to go onto this single magnetic site because this one, the magnetic moment here is pointing up. It likes this electron, but it doesn't like that one. Okay? So if you like, this type of pairing on top of this particular site would be suppressed, would be very, very reduced. But now if I have these two pairs and if I have an angle between these two sites, this electron can go here and this electron can go there. It's not a perfect situation because it's not an antiferromagnetic alignment like I have here. But this angle between these guys and these Cooper pair makes it possible to basically create Cooper pairing in which the electron pairs up not on a given site, but on sites that are near one another. Okay? So,
wouldn't the Cooper pair have to be pretty small to take advantage of your favorite site? I mean, the coherence lengths are much bigger.
Exactly. So this is a very, very rough picture, but we have a call coming in. I think somebody's asking a question. That's right. So this is a sort of a local picture, but you want to think about this as a long wavelength problem. So we kind of played around with this idea theoretically, and it looked like it was going to work. Of course, this is not the experiment, but this was just a warm-up to the experiment. We basically consider our helix, and we do a calculation with Andre, and Stefan, my postdoc, and really actually learned from Andre how to do these calculations. And to our delight, we found that if you could make this helical texture structure, if you could make it, it would indeed, theoretically, you would find that so the superconductor that's underneath has an energy gap that's this big, very large. All these things inside are those excitations which are basically particle and hole symmetric. And this thing in the middle is the thing that shows up at the end of the chain, and you can take basically a two-dimensional map of where this peak would be, and it would be stuck to the edge of the system. Okay. These are the Shiba states in the middle. Okay. Well, this was calculated just looking at the edge. So this is at the edge, this is in the middle. Okay. But as you pointed out, this is kind of a very unrealistic model in some sense. And what's also very perhaps unrealistic is the fact that you would just be able to, in the lab, make such a specific magnetic structure with a helical pitch. But what about just the ferromagnet? Okay? So I just told you the case where the spins were up was bad, right? So what does a ferromagnet do? Well, it takes the bands of electrons moving along this chain, energy versus momentum, and basically splits them by the exchange interaction. So this is what we call the majority band. This is called the minority band. Okay? And this is the exchange interaction between them. Now, normally, nobody in their right mind would think that you can put this next to an S-wave superconductor and you will get superconductivity. This is a magnet, and this is a superconductor, the opposite. But now, it turns out that if your superconductor has this strong spin-orbit coupling, which means what? Which means that let's say the atoms inside the superconductor are heavy, okay? When an electron moves around the superconductor, okay, when it moves as a function of its momentum, it's basically the spin of the electron depends on the momentum of the electron. The two are coupled together. So what that does is that if you like this picture where I have put this spin up everywhere along this band, this spin actually is not always up. It actually tilts as a function of k. And that's great because if I have a tilt here and a tilt there pointing in two different directions at the chemical potential, that allows me to basically pair electrons in this otherwise unpairable ferromagnet. So this was kind of the key idea, that you don't need just ferromagnetism, which is just forces you to sort of expel the possibility of pairing on site, but you have this pairing which is happening because of spin-orbit coupling, and because this is happening in longer length, answering David's question, is something that could happen, for example, at a wave vector which is very different. All right. Then came another surprise. The other surprise, theoretically, was that if you were managed to make this object, it will always be topological superconductor. Okay? And the reason for that is this. If you go back to Kitaev's recipe, Kitaev basically said, give me spinless electrons. Well, if this band stays all the way down here, okay, and is far away from the band that's near the chemical potential, which is relevant for superconductivity, basically you only have one species of electron spins that you're making a superconductor out of. And therefore, this is going to be always topological. And basically, what that depends on is how far apart are these two bands from one another. And the larger they are apart from one another, well, the harder it is to pair them. You need that spin-orbit coupling to help you. But if you manage to pair them, it will always be topological. So this point is pretty much now agreed upon by people working on the theory of these chains. And now let me tell you about the experiments. So to do these experiments, you need a number of things. You need to be able to create a very clean superconductor. You need to be able to create a chain of magnetic atoms. You need to convince yourself that you understand the magnetism of these chains. Do you have the right conditions? Or is it ferromagnet? Do you have this thing, the spin-orbit coupling? And all these pieces have to come together. So this takes very sophisticated equipment that allows you to do in situ growth in ultra-high vacuum environment. It allows you to transfer the sample without exposure to air to a very good low temperature STM machine that gives you high energy resolution. It also, you need to have the ability to do magnetic measurements on the same structures. So all these different things have to come together to basically be able to do this one single experiment. Okay, so this has been kind of a tough road. So let me tell you about the pieces. So first you need a superconductor to build your wire out of, on top of. And you need a superconductor that has strong spin-orbit coupling. So lead. Lead is like one of the most well-understood BCS conventional superconductors. You can basically prepare a crystal of lead to be free of atomic defects. And this is the surface of lead. This is about, I forget how big it is. I think it's like a few hundred nanometers. And if you zoom in, you know, basically the lead atoms sitting perfectly on top of the surface. Now, you notice that I chose a very funny face of lead. And the reason we chose this funny face of lead is that we want to make one-dimensional structures. And this funny face of lead basically has these rows of atoms that gives us a template upon which we can basically create our one-dimensional structures. And the way we do that is very simple. Well, it was lucky that it worked, but we were inspired by some people's experiment doing self-assembly of atoms on surfaces, but it's very simple. You take this lead and evaporate iron atoms on top of it at room temperature and anneal it just a little bit. Initially, the iron atoms basically make these blobs, And if you anneal it just a little bit, the mobility of atoms is such that they just run around the lead surface, and because they see one direction which is easy, they basically make this one-dimensional chain. Okay? So they are self-assembled iron atoms, basically embedded on the surface of lead.
We were seeing multiple terraces in the previous picture.
Yeah, these are multiple terraces. Thank you. So this is like one atomic terrace. This is another atomic terrace. That's the same thing as this one. And then in the middle of a very flat terrace, which can be 20, 30 nanometer wide, you can create one of these one-dimensional chains. Now, if you look carefully at this higher resolution image, you see that the sort of the peak of this mountain, if you like, is sort of sitting between these rows underneath. Those are the rows of the lead atom underneath, and you have laid basically this iron chain in between those rows. Now, all right, what's the magnetism like? Okay, so this took us a while. Then we had to figure out how to measure the magnetism. So now there are folks in our community which do scanning tunneling microscopy, which use the STM to measure magnetism on the atomic scale. And the way this works is that you take your tip and you coat it with some magnetic material. And if you have a magnetic sample, basically the tunneling of electrons between your magnetic tip and your magnetic sample is going to depend on the orientation of the magnetism in your tip and in the magnetism in your sample. If the two are aligned, you get good tunneling current. If you're anti-aligned, you get less or get nothing. So this is the GMR effect which we use in reading magnetic heads. But here you're doing it on the atomic scale. Okay? And in this instrument, we also have the ability to apply a magnetic field to sort of dial in the orientation of the probing tip in the direction we like. Okay, this turns out to be very critical. So using this instrument, we can basically now go around, once we have a magnetic tip, and detect the signal. Is the spin of the tip aligned with the spin of the sample, the magnetic moment, or is it anti-aligned? So you go around. I showed you one particular chain. But if you look around the surface, there are chains everywhere. They're self-assembled in all different areas. So you just take one chain and do this experiment and go to the next chain and so on. And the color scale here represents that signal, which is either high or low, and it's spatially resolved as well, which is telling you basically this is aligned with the tip, this is anti-aligned, aligned with the tip, and anti-aligned. So these are different chains. 50% of them are up, and 50% of them are down, just what you would expect. And you can flip your tip and repeat the experiment on the same chain just to feel confident that you're really dealing with what looks like a ferromagnet. So good.
The electrons are localized to the iron atoms?
So that's a good question. We believe that these chains are closely packed enough that they basically have, you can talk about the band structure of this iron chain. But you cannot talk about it in isolation. It's coupled to the lead underneath. So you have those bands that I kind of roughly draw for you for a simple ferromagnet. But think about them and blurring them because they're coupled to another material which is non-magnetic and a different material.
Are you doing this at half the TC of the lead? Or what?
This experiment can be done at any temperature you like, but these experiments were done with application of a magnetic field, so lead was basically normal. But that will become interesting in a second. What happens if the lead is superconducting and you're probing magnetism at the same time? Feel free to ask questions.
How long would how many atoms?
How many atoms? So let's see. We believe the distance between the iron atoms is about 2 angstroms. So we have a lot of atoms there. Okay. Any other questions? Okay, great. Okay, but that was just one piece of our requirement. One piece of our requirement was just to have a ferromagnet. But how are we going to get electrons to have their spin change as a function of momentum? Is you have to have some sort of, well, maybe the magnetism is not uniform. But the lead underneath has this property where the electrons are, the spin of the electrons and the momentum of the electrons are strongly locked together. And we actually found a very good surprise that we could actually measure this effect using our instrument. So remember, I have this magnetic tip, right? But lead is not a magnet, right? But what does spin-orbit coupling tell you? Well, the spin-orbit coupling tells you that the momentum of the electron and the spin care about one another. When you break inversion symmetry at the surface, typically what that does, it basically forces the electron spin to be in the plane that you have broken the inversion symmetry about. Okay? It doesn't like to be out of the plane. Okay? So this is kind of Rashba type interaction at the surface, which is very common in most materials. So what does that mean? It means that if you come in with tunneling electrons from your tip, if its axis of tunneling is basically aligned with that of a surface, you get more tunneling than if it's perpendicular to the surface. And in fact, this is what we found in this experiment, where we tunneling, measuring the tunneling rate as a function of application of a magnetic field, which is out of the plane. And as we polarize the spin of the tip out of the plane, basically the tunneling rate goes down, telling you that the electron in the surface like to keep their spin in plane. So this is a nice experimental just observation of spin-orbit coupling without any theory. Okay, so it looks like we have all the ingredients. We have a one-dimensional chain of magnetic atoms. We have ferromagnetism. We have strong spin-orbit coupling. So if the theory is correct, if you manage to get superconductivity on these chains, then you should have a Maya Rana zero mode. So the advantage of the STM, of course, is that we can go to these chains, and we can go to both ends of these chains, for example. So this is a chain with, they do actually often have defects in the middle of them. And you can do experiments where you can put your tip at different locations. So here's the measurement, measured just outside the chain on the superconducting lead. And this is the energy gap of lead. There are no in-gap quasi-particle state. This is kind of our vacuum inside of which we are basically building this object. And now, as we come onto the chain, climb onto the chain, at every pixel, at every fraction of an angstrom, we can basically record what the electronic states are doing as a function of energy. Okay? Right away, you see that when you're in the middle of the chain, you have this suppression, which is associated with the fact that superconductivity has creeped in on top of our chain. Well, it's not as good as the lead outside, okay, because you have magnetism and other things going on this chain. But the suppression that you see here is indicative of superconductivity. Now you see, I'm sorry? Zero field, no magnetic field applied. In fact, that's a good question that will come in later for a diagnostic tool. And you can see that there are these peaks and other things going on, for example, inside the chain. And these are what you would expect if you create these localized particles, well, not localized anymore, they're running along the chain. They're basically these states that are not your Maya Ranas, but they are created inside the gap of the superconductor by the magnet. So let me show you these slices of that movie here, where I focus in the middle. This is the superconductivity in the middle of the chain. And I focus at the two ends of the same chain. And this is where we see a zero energy peak basically very clearly observed. This is in the original experiments which were done at 1.4 Kelvin. Okay? Now, let me show you this data a little bit differently, which is that if you look at the height of these curves, I've turned them into a color, and I've plotted them as a function of position as you move along this chain. Okay? So essentially, you can see that this is the superconductor outside. Okay? So this is telling you that here you have vacuum, no particles at this energy range. Inside here, inside the chain, you have all kinds of particles that are basically bound to this chain. And this peak that you see here at the end and on the other end is basically corresponding to this peak. And this is basically what we were looking for, which is this zero energy state, which is associated with the end of the chain. And what's interesting about this zero energy state is that it just comes out of nowhere. It's not connected to other states as you basically, for example, look at these states. They kind of move around. They look like they are a continuation of these states that are being modified by the end of the chain. So this is a critical, it's a very critical thing to observe in the experiment. Now, of course, what we can do is now we can turn the microscope into a different mode of operation where we say, OK, show me what particles do at different energies and take a spatial map. And this is what all the different, basically, quasi-particles are doing at different energies. And this is what they're doing at 0 energy. Okay? You see a very well localized state that's living basically at the very end of these chains. And this happens basically at the end of almost every chain we have constructed using this technique.
And can you break the chain in the middle and then look at it again?
No. The problem is that lead is very soft. And when we try to interact with the lead with the STM tip, we often just mess up the whole experiment.
So how would you change it in the absence of superconductivity?
Excellent question. Give me 2 slides. So first is how good is your 0, right? Because if we want to talk about these particles and antiparticles, well, your ability to resolve this 0 is very important. It could be just 2 peaks, particle, antiparticle, hole-like, electron-like state, just very, very close to 0 energy. You just can't resolve them in your experiment. So we spend about a year, maybe a year and a half, to push this experiment in a new instrument to 20 millikelvin. Our electrons are unfortunately not super cold. This is actually work led by Ben, proud graduate. And basically, he was able to show that within the resolution of this experiment, within 45 micro eV, basically these particles are bound to 0 energy. There are some STM experts here from Jenny Hoffman's group, and they probably could tell you that it's very, very hard to push this much further in the STM world to get this to even better resolution. Okay, so we are almost at the edge of what is possible with our technique.
You're obviously not in equilibrium because the electrons seem to have different temperature in the center.
Okay, that's a good question. So the problem actually seems to be not the electrons in the sample, but more the electrons in our tip. The tip is just a giant, beautiful antenna, which is picking up radiation from everywhere. And we can't supercool this tip because you want to supercool a piece of metal, it's good to just ground it. And we can't ground these and measure current through this wire at the same time. Question about, is it there in the absence of superconductivity? And a question that was asked earlier, there are tons of other things that could give you 0 bias peak in these type of measurement. And the most prominent one is so-called the Kondo effect, in which you basically electrons collectively decide we have an extra spin in this piece of metal. We're going to screen this piece of this spin. And they do that by creating a cloud, which is measured as a many-body quasi-particle peak, as a peak at 0 energy, at the Fermi energy. So this could be an explanation for many of these experiments, especially if you're weakening superconductivity by putting magnetism or applying a magnetic field. So we just got rid of superconductivity by just applying a very small magnetic field, which is just 100 millitesla. And once you close that superconducting gap, everything goes away. Once you have no superconductivity, you have no features in the data whatsoever. Okay? This just looks like basically a piece of magnet. We can do measurements to show that it is a piece of magnet with nothing very exciting going on in it. So you need superconductivity to create these particles that are showing up as in-gap states and that 0 energy states. Okay. How am I doing on time? Perfect. So these experiments have been reproduced now by other groups in Berlin and in Basel. STM and AFM groups have reproduced these experiments. And let me tell you a couple of things that we are working on now, further tests, and then give you a sort of a flavor of where we are going longer term. So one important signature that's actually been predicted theoretically we keep talking about this electron-hole mixtures being equal. Okay, it turns out, well, in our experiment, it just shows up at a zero energy peak. So how can you tell it's just both half electron and half hole? You know, just because it happens to be at zero. And it turns out that there is an experiment that was proposed, and I think one of the co-authors of this paper is postdoc here, Falco, and which is you use a superconducting tip to probe this superconducting sample, which has the chain on top of it. So these two components of the electron, the whole part of this Maya Rana state, can be measured by basically flipping the switch between tunneling at voltage positive and voltage negative into using a superconducting tip. And the idea is the following. When you have a superconducting tip and a superconducting sample, when you try to tunnel between one and the other, you can't do it unless you overcome the gap of the superconductor in the tip and overcome the gap of the superconductor in the sample. Okay, so the tunneling looks like this. So you get this characteristic spectra, which you can measure both at putting a positive bias on the tip or a positive bias on the sample. But it turns out that now if you have a Maya Rana happening in your sample, this would happen at an energy corresponding to the gap of the tip, not at zero energy. And the measurement done at one bias and another basically gives you a measure of this ratio of these two components. So here's the experiment. You basically use a superconducting tip. You go to the location where we see a Maya Rana signal. And no longer our Maya Rana signal appears at zero bias, because in order to do that, in order to detect it, you have to overcome the gap, the superconducting gap in the tip. So it occurs at another energy. And you can compare what that signal looks like when you go to positive energy on the tip or positive energy on the sample. And what you notice is that basically there are all these other states that we've been looking at. They show a lot of asymmetry between those two measurements. But this thing right at that energy is really dead on top of one another. So this is a nice confirmation that what we are dealing with is an equal mixture of electrons and holes, which needs to be. If this wasn't the case, then you would say, OK, this is another spurious peak. What are the other signatures we could look for? Well, it turns out the Maya Rana spin, it's a funny object. It has some spin properties that are very unusual. So let me tell you why. So let's just think about a object that is its own antiparticle. And remember, I didn't put any spin index in the previous mixture of electrons and holes. So this is an electron, this is a hole. But if this to be true, the spin index on these two pieces would have to be the same. Because if I take a conjugate of this, basically I have to end up with exactly the same thing. And you contrast this to what happens to the normal type of particles that live inside the superconducting gap. They are made out of electrons and holes, just like we talked about, but they are made out of different spin index in time reverse states. And this is very different for a Maya Rana. So it turns out that this is what we are right now working on, motivated by some experiments with spin polarized measurement. It turns out that the Maya Ranas actually have a very unique signature in this. They don't have a spin. The spin is not a good quantum number because of spin-orbit coupling, but the spin expectation value is something that defines the Maya Rana uniquely relative to other types of electronic states that you can have at near zero energy. All right. But ultimately, it's not just the detection that these things exist inside materials, whether our platform or the semiconductor platform. Amir and Bert are also working on other types of platform using, for example, two-dimensional strong spin orbit coupled semiconductors. Ultimately, what we have to do is we have to find ways to move them and hopefully braid them. And this would be the ultimate test and very new physics being able to do that. So we have some harebrained scheme of our own, and we're having just fun with the theorists. For example, if we didn't make chains, but we made rings, okay? And can you make rings of magnetic atoms on surfaces? Well, there was a guy I worked with once who did this experiment, and It's almost, I think, on the cover of every, it's in every, I think, introductory physics book, this picture. So these are iron atoms on copper. So if we could engineer these type of structures, it turns out that, well, you will have no edge, right? But it will still be topological. And if you can dynamically create edge by putting like perturbation like magnetic fields, theoretically, we believe it's possible to at least create sections of these chains where you have topological and non-topological phases. If you could do this and rotate the magnetic field, I would be very happy, because I think, but of course, my theorist friends are not happy with that. They want to do even more fantastic things, interpenetrating rings. And if you could make interpenetrating rings, and if you could rotate the magnetic field with the right ratio, you can create a very strange braiding of these Maya Ranas in our chains. All right, so this brings me to the end of my story about our experiment. So what's the story with the Maya Rana, the man? So soon after our paper got published, we heard that the case of Maya Rana is closed. And I don't know, how good is your Italian? How good is your Italian, Bob? Bad. So if you put this into Google Translate, it will tell you that the case was closed because there was new evidence of a picture that was found from a relative of Maya Rana. And apparently he has a lot of relatives still who got postcards from him. And apparently there was a postcard from 1958, roughly, from Venezuela. So you see that the weird thing about Maya Rana is that he withdrew all the money from his bank account just before he disappeared. So there is a very strong sense that he went somewhere and had a good life. So I started digging into this. And the evidence is this picture. So now here's a test. Which one is Maya Rana? Come on, guys. After an hour of me talking, where is Maya Rana? Wolfgang, you want to take a gander? There you go. It's the Maya Rana is always the guy at the end. And they really did this analysis, which is horrible, but that's the case. But on a more serious note, let me just end this talk by saying, I think we're almost out of time. So I think this is an example of a situation where you engineer the material to have very specific interactions to create some very exotic physics. I think that that's what's exciting about this whole field of topological phases, that we are finding new ways to think about how we can engineer materials or create new materials using chemistry to find exotic physics in materials. So with that, I stop and take any questions you have.
So before we begin with questions, I'd like to ask that you wait until a microphone reaches you, because these talks are recorded, and we want to get your question on tape.
Oh, no.
So, any questions?
So it seems that you're in the center of the wire, your Shiva states seem to be more intense on one bias than the other. Is that consistent, and do you understand that?
Yeah. So, let's think about just the Anderson model of an impurity. So what makes it the impurity is you have one level occupied and one level unoccupied, right? So just for a single impurity site, if you have your Fermi energy, and let's say the upper level is closer to the chemical potential, or versus the lower level is closest to the chemical potential, this is an asymmetric situation, both of which impurities are magnetic, but it makes the electron and the whole component of these bound states have different weight. So that's a very simple way of understanding. It basically has to do with where the chemical potentials sit relative to the original.
It's the same on all the wires?
Yes, it's always the same. These wires are all basically created equal. Question?
So your Maya Ranas are 0 plus 1 dimensional. Of course, Maya Rana was thinking about propagating Maya Rana fermions.
Yeah.
So do you have any comments
these are
about
zero
that?
mode. These are zero
Is there
dimensional.
any reason to want to do higher dimensional ones, or do we
Thank
already
you.
have them, or I don't know?
So if you extended this chain to make a ring, not a ring, I'm sorry, an island, and you have this same kind of spin texture on the island, you will create what we call a P plus IP superconductor. And then the Maya Ranas at the end would basically have a dispersion that is running in one direction. So those would be dispersing Maya Ranas. But if you're interested in this quantum information aspect, those are very hard to think about how you would braid. But yes, that's actually something we are very interested in, creating two-dimensional version of this. And so is, I think, this guy.
So what happens as you raise the temperature of the system? Do you know when they go away, or
Well,
is it difficult to follow?
as you get rid of superconductivity, basically all of these things go away. So, but as a function of temperature, these are not very good experiments for our probe because it just messes up our energy resolution. We just tend to go down in temperature and use other knobs, like magnetic field.
Great talk, thanks. I was wondering, you mentioned that you in this this new low temperature setup, you measure the localized zero energy to within 45 micro UV. Is that always on one side of zero, or I mean, do they always appear at the same?
They always
value?
appear at zero. So there's sometimes some offset in the electrometer, as you well know.
Right.
Which you have
I'm
to-
wondering if it's that, if the offset is constant.
Yeah. Well, this is one example. Yeah. So the background that's coming from these states, which actually broadens these spectra, is electron hole asymmetric. So that contributes a little bit to the shape of this curve. But you can, if you wanted to do a fitting job and think about the background, you can convince yourself it's at zero, because it turns out that all the other peaks come in pairs. Even though their amplitude is different, all the other in-gap states are always like, you just can fold it on top of one another, and they look like they're basically partners, except that one.
Mm-hmm.
All right. I think we've exhausted Ali. Thank you very much.
I just.